All right, welcome back. Today, we're diving into a new AI model that could completely flip the script on how we build intelligent systems. And get this, it's built on a blueprint that's, well, surprisingly familiar. It's a question that drives people in AI nuts. How can these incredibly powerful multi-billion-dollar AI models write beautiful poetry, but then completely fall apart on a simple logic puzzle? It just doesn't make sense. And that question, it really gets to the heart of one of the biggest hurdles in AI right now. So, to really get why this new model is such a big deal, we first have to talk about the problem. And the problem, well, it lies with the current kings of the hill, the large language models. LLMs. It sounds kind of weird, right? I mean, these models have billions of parameters, but their core design, what we call their architecture, is actually paradoxically shallow. Now, that shallow design is amazing for generating human-like text, but it creates this hard limit, the ceiling, on their ability to do the kind of deep, step-by-step thinking that we humans do without even, well, thinking about it. So how do they get around this limitation? How do they sort of fake real reasoning? Well, they use a trick called chain of thought, or COT. Basically, you force the model to talk through the problem, to write out every single step. It's like turning a logic puzzle into an essay question. Imagine having to narrate every single step of a math problem out loud just to solve it. That's kind of what's happening here. But as the researchers behind this new model say so perfectly, this chain of thought stuff, it's just a crutch. It's not a real solution. It's super brittle. I mean, one tiny mistake in the text and the whole chain of logic just collapses. Plus, it's incredibly slow and inefficient. And this gets to the real core of the issue. There's a huge difference between externalizing your thoughts, writing them all out, and what these researchers call latent reasoning. That's the ability to actually think inside a hidden internal space. Like we do. We don't have to narrate our every thought to come to a conclusion. We just think. Okay, so if the current way of building these models is the problem, where do you look for a better design? The answer is pretty obvious when you think about it. You look at the best, most efficient reasoning machine ever created, the human brain. The researchers really honed in on three key ideas from how our brains work. First, there's hierarchical processing, the fact that different parts of our brain handle different kinds of thinking, from high-level ideas to nitty-gritty details. Then there's temporal separation, which just means these different parts operate at different speeds. And finally, recurrent connectivity, which is just a fancy way of saying our brains use feedback loops to circle back and refine an idea until it's right. So, armed with this blueprint from the brain, the team went and built something totally new. It's called the Hierarchical Reasoning Model, or HRM for short. And yeah, if the giant LLMs are the Goliaths of the AI world, this little guy is definitely David. So, how does it work? Well, HRM has two main parts that talk to each other. There's a high-level module that's like a planner. It operates slowly, thinks about the big picture strategy. Then it hands off tasks to a low-level module, which crunches the numbers and does the fast, detailed work. Does that sound familiar? It should. It's a direct copy of that brain blueprint we just talked about. And here is the absolute kicker. Get this. The entire HRM model is just 27 million parameters. No, that is not a typo. We're talking thousands of times smaller than the massive language models it's about to compete with. It's tiny. All right, so the stage is set for this epic David and Goliath showdown. The question is, how does this tiny, brain-inspired model actually stack up against the giants, especially on puzzles that are designed to be their kryptonite? Okay, first up to bat, a super hard Sudoku puzzle. And the results are, honestly, they're staggering. Just look at this. The big, state-of-the-art models, they score 0. A big fat 0. They cannot solve a single one. And then there's HRM. Trained on just 1,000 examples, it solves over 55% of them. It's not even a competition. So you might be thinking, okay, maybe Sudoku was just a fluke, right? Well, let's look at another test. Finding the shortest path through a really complex maze. And it's the exact same story. The giants? 0. They get completely lost. HRM, it finds the perfect path almost 75% of the time. This is a pattern. Okay, what about a more general test of raw intelligence? Let's look at the ARC-AGI benchmark. This thing is famously difficult. It tests abstract reasoning. And even here, our tiny 27 million parameter HRM comes out on top. It beats models that are literally thousands of times bigger. So what does all this mean? What's the big takeaway? It's not just that HRM is a little bit better. No, it's showing a fundamentally different kind of skill. It's way more efficient, it needs a tiny, tiny fraction of the training data, and it succeeds in the exact places where the old strategy of just make the models bigger has totally hit a wall. So, how is this even possible? How did the underdog pull this off? To get that, we need to pop the hood and look at its secret weapon, which is a totally unique way of thinking internally. The magic behind it all is a process they call hierarchical convergence. And the best way to think about it is like a CEO and their engineering team. The high-level module, that's the CEO, sets a big picture goal. The low-level module, that's the team, gets to work, crunches the numbers, and reports back. Then the CEO takes that info and sets the next goal. It's this back-and-forth cycle of planning and doing that lets the model solve complex problems internally without having to write it all down. And what's really cool is how it learns. It's super efficient. You see, with most models, the longer the problem, the more memory they eat up. It's a huge bottleneck. But HRM's memory use stays constant. It stays flat. That makes it way more efficient and, a lot more like how a real biological brain seems to handle things. But here's where the story gets really wild. This is where it goes from just being a clever piece of engineering to something profound. Because while it was learning to solve these puzzles, the model spontaneously organized itself in a way that looks almost exactly like a real brain. So in neuroscience, there's this known principle that higher-level parts of the brain, the parts that do abstract thinking, operate in a higher dimensional space. It's a more complex workspace, basically. And guess what? That is exactly what happened inside HRM, all by itself. The high-level planner module evolved to have a much higher dimensional space than the low-level worker. Nobody programmed it to do that. It just happened. And you want to know how close this parallel is? The ratio between the high and low-level modules in HRM came out to 2.98. Well, scientists have measured that same ratio in a mouse's brain, and it's around 2.25. It's a stunningly close match. It's like we're seeing convergent evolution happen between biology and silicon. Look, this is way bigger than just solving Sudoku or mazes. What these findings do is challenge the main belief in AI today. They basically scream that the path forward to truly smart, robust AI might not be about building bigger and bigger models. It might be about building smarter, brain-inspired models. Think about it. HRM learned a fundamental principle of how brains are organized, all on its own. It learned how to think more efficiently. And that leaves us with one final, really big question. If an AI can learn to organize itself like a brain and reason like a brain, what else can it learn to do?